So, first of all, thanks. I would like to thank the organizers for this opportunity. So today I'm going to talk about the Hierarchion, which is just a Relaxant model, which where the different elements of the Relaxant mechanism are also used to solve the other hierarchies in the standard model. So of course you solve the Higgs mass, but we also address flavor, so the masses and mixing of the leptons and quarks, and also also neutrinos, if you want to consider this beyond standard models. But anyway, this is kind of together. And also we address the strong CP problem. So in one framework, hopefully it won't seem to like we are putting everything together, but it kind of fits organically. So what is it? It's a Relaxant model with Clockwork. So it's a Clockwork Relaxant model where the different ingredients are identified with so for example, the phi shift symmetry is a U1 Froggatt-Nielsen flavor symmetry, which can explain the quark masses and mixings and the lepton masses and mixings. The back reaction comes from sterile neutrinos, from TeV scales sterile neutrinos. So unlike other Relaxant models, unlike most other Relaxant models, we don't have electroweak charged states at TeV scale, because our back reaction is basically the standard model plus the sterile neutrinos. And finally, the final phase where the Relaxant stops, which is as you would know, it's order 1. So this we will identify with the secm phase. The heavy ones are very heavy, tend to at the scale of f, which is 10 to the 10 or something. So yeah, okay. So you mean to generate the? I will come to that. So okay. So I mean, this is of course very vague for. So I should give an introduction to Relaxant and Clockwork, but since there have been talks here, I'll try to be brief about this, because the model is really about these other elements. So I will. The Relaxant Clockwork part is more or less the same as any other, is the usual story. So let me quickly give a very brief sketch of the Relaxant mechanism, putting emphasis on the points we would need later. So basic ingredients. So I should say Relaxant Clockwork ingredients. So as many of you would know, the Relaxant model, you have to start with some Goldstone boson, which becomes a pseudo Goldstone boson because you break its shift symmetry twice. First by what I will call, or what you can call, a rolling sector. So here you break the shift symmetry and you generate some kind of potential. So the potential is something like okay, so this is the potential. Basically, as you see, that the mu square of the Higgs depends on the value of the Relaxant field, and the Relaxant has a potential which goes like, so if I plot this, it's just something like, it's a cosine, so it goes like this. And there is an interesting so let me call phi equal to phi c, where the point where cos phi c over f is kappa. So this is kappa, which is an order 1 number. It can be anything. So it should be less than order 1, otherwise you can't have cosine. It should be less than 1, but order 1. So cosine, so above this point, the cosine is bigger than kappa. So you see that the mu squared is positive, and below this, to the right, the mu squared is negative. So here mu squared is more than 0, and you have so I should say, so the basic idea is that there is a field which slowly rolls during inflation, like this. So it starts somewhere here where mu squared is positive, and electroweak symmetry is preserved. And here, after this point, electroweak symmetry broken. Okay. Now, after it breaks, the second important ingredient of the relaxation mechanism, which is the back reaction sector, it comes into play. So in my model, I'll tell you how exactly all these terms are generated and so on. But right now, just let me sketch what it is like. So this back reaction sector is something like, let's put. So this M tilde is some. It's usually some explicit breaking of the shift symmetry, and it's something. Usually, it has to be in general. It is in usual models. It's less than, let's say, 4 pi v. It's something weak scale, and this F periodicity is has to be much smaller than F, as I'll show very soon.
The condition there is capital F, not cos pi c or by
sorry. Thank you. So this is capital F. Yeah, sorry. So this small f is much smaller. So what it causes is it makes wiggles like this. So the amplitude of these things is proportional. It grows with v. So this is proportional to v squared. So at this point, the amplitude starts very small because mu squared is exactly 0, and then as mu squared becomes more and more negative, the amplitude increases. So this is the basic picture. Now the relaxation is it's slowly rolling. So the equation of motion is something like. So it will stop when it reaches a minimum of the. Classically speaking, at the classical level, it will stop when v prime phi is 0. So now, when is this 0? So you can just minimize the potential. The two important terms are this one and this one. So yeah. So sorry, I should mention this is the Hubble. So once you minimize, you get a very something like this. So let's say the point where this is satisfied, I call it phi 0, is equal to lambda. Now, also if you think about it carefully, both these phases are order 1. So it's clear that the sine phi over f has to be order 1 because you stop somewhere here and not at an arbitrary point if you don't. And also this, I mean, there are minimas with all kinds of sine phi, but the first ones it will encounter the sine phi 0 over f is big, so it will stop at an order 1 phase. So this is going to be important. So maybe I'll just highlight. So in your in our low energy Lagrangian, we'll have factors of both phi 0 over small f and over big F, and both these are order 1. So this I will call let's say so at this now at this, maybe I should have mentioned already at this stage. So the way we will solve the strong CP problem is using what is called the Nelson bar mechanism. So we are just going to, so this is really a combination of existing models and we are putting it together. So we'll take so what happens in Nelson bar models is that you assume that CP is a good symmetry. So I should mention it here. CP is a good symmetry and it is spontaneously broken. So at some scale it's spontaneously broken by the wave of some field. So in our case it will be the last scalar of the clockwork, by which I'm going to come to. But if some field gets an imaginary wave, okay. So and this if you can arrange it so that this phase becomes the secant phase. So at this scale you have the secant phase, or maybe more correctly you say you generate a Yarlskog determinant or something, or you have a phase in the matrix, and then this is order 1, the phase is order 1, and then but you have to be sure that theta QCD is very small. And this is really the challenge. I mean, you will see it's quite smaller than 10 to the minus 10 or whatever. And then once you do this, after this, the running is very small, because it was showed by, I think, Ellis and Gaillard that this running from, the opposite, from CKM to QCD is a 7-loop effect. So it's very small effect. So even if you can set this at a scale of, let's say, 10 to the 10 GeV or something, then it won't be you can show that the theta QCD is small at the low scale. So because we want CP to be a good symmetry, all the coupling, so if you see a Yukawa coupling in my Lagrangian, everything is real and CP conserving, and the only CP breaking things will come from powers of this and this, from powers of these two kind of phases. Okay, so that's the first thing. But the second thing, important thing, is that from here you get a condition on you see that the cutoff goes as F over F, where this M tilde is also weak scale. So you see that for a successful relaxant model to raise the cutoff a lot, you need a huge F over small f. So for example, if you want to raise lambda to, let's say, 10 to the 8 GeV as an example, then you can do the calculation. So your F over F has to be order 10 to the 20. So now how do we get such huge hierarchies of periodicities? And you can, if you think about it, this really translates to a hierarchy of the charges that break the shift symmetry in the rolling sector and the back reaction sector. So I would say generically this seems very, very hard to achieve, but this is why we need the clockwork. So maybe maybe I can. Okay, we'll use this one. So again, I'll be very brief about the clockwork because there have been other talks here. Okay, so clockwork is just a theory. So a theory of many scalars. Maybe I'll make it like that. So it's a theory of many scalars where the scalars, so this will be my notation for charge of any field. So the field phi I has a charge 1 over 3 to the I. And then so these are complex fields, and you give all of them a wave by a very simple potential. So this is for simplicity, I think you can deform this, but okay, and then you add a term which is like and everything is summed over I. So so you assume first of all that epsilon is a bit smaller than lambda, so I can ignore this part at first, and if you ignore this part, you see that all of these fields get a wave. So all of these fields get a wave f, let's say, and I can write these fields in the low energy like something like. Okay, so so below the scale of the radial modes, I can write these fields like this, and then if you just substitute it here, now I use this term. If I just substitute it here, I get a potential for these pi's, which are the angular parts of each phi. So which is like something like this. I might be missing some factors. So now this is the potential. I can diagonalize the mass matrix of these pi's, and what you find is that there is still one, and this is the most important thing, which is the only thing that I would use, is that you find that you still have an unbroken U1, which you could already guess from here. And this unbroken U1, there's a Goldstone. So the lightest mode here, which is something like this. So the lightest mode, and you could have guessed this from the charges in the beginning, is something like this, which has a. So now I don't need. Yeah. Okay, so this lightest mode from here you see has an overlap, has an order 1 overlap with the first site, and an exponentially small overlap with the last site. Okay, so now what I want to do is now it's very it's not you can now generate the relaxant potential. If I now put some explicit breaking here and generate a term like, let's say, F, and okay, maybe I should make it somewhere here. So let's say this is my phi n, and then I can also break, and I will, in our model, I'll show you how these terms arise. So then I can have phi n Okay, so I generate these terms by some explicit breaking at the edges, and this explicit breaking is again smaller than I rubbed it, but the epsilon. So you can do this systematically. First you ignore epsilon, and then think that there's only lambda in the potential. Then you put the epsilon and derive this, and then I break it. It's even smaller effect, so it's all consistent. Now you see I can use this fact that the overlap is the mixing angles of the relaxion, the overlap at pi 0 and I should write pi n. Sorry. And then you see that, so I should be normalizing. It's something like 8/9 or something, but I will ignore this. So I can just say up to this factor, it's just, I can write the pi naught as now a linear combination of the mass eigenstates, and the lightest one I just write is phi. Yeah, also it's true that you can show that all the other pseudo Goldstone, so this is one linear combination, is one of the mass eigenstates. All the other n mass eigenstates, their wave is 0. This is kind of important to show that there is no other spontaneous CP violation. So you could have started from that Lagrangian and shown that. So then I can project to the relaxation mode here and also here. So I get phi over 3 to the n and phi over 3 to the n. Now if n is large enough, I can call f 3 to the nf. And then you see I have a big F here and a big F here. So with an n large enough, I can have this hierarchy of things, and now I have a potential just like the one I started with. And this can, with a large enough n, this can raise the cutoff. Okay, so this is the brief review, and now let me tell you what is the structure of our model. Okay, but I need this chain, then I'll go to the upper bound. So, yeah, no, but I need to use this first line, and then I'll go to the.
You can write on the back one even if it's up. That's what they're saying.
Okay, I see. Okay, you're right. Okay, maybe this is good. Okay, so now let me again. So this is like the important cartoon of our model. So what we are going to do is the phi 0 would become the flavon for in the Froggatt-Nielsen mechanism for the quark masses and the lepton masses, and so at this side I will put quark plus lepton Yukawas. Plus, I'm also going to break the Froggatt-Nielsen symmetry by adding by Majorana masses of sterile neutrinos at the TeV scale. which will generate the back reaction for me. And okay, this is number one. And at this nth site, and this I'll explain, this phi n will become the field whose wave becomes breaks CP spontaneously. I mean, CP is spontaneously broken at both, so you have two phases, as you know, but this one is a harmless phase that will enter the neutrino sector, and we don't care about it. As you will see, the quarks will kind of couple also, not to the Yukawa, but through another term to phi n, and then the phase of the phi n will enter the quark mass matrix. So here I'll have my Nelson bar. Sorry? I will tell you, because here you will see there's some the potential you generate, it's hard to cut it off at the weak scale because of this. Yeah.
Principle, all the interesting potential energies are complex as in the most general scenario. How many irrotatable phases do we get in general?
In the clockwork, you mean?
In the clockwork, if you count how many phases are irrotated, how many of them you cannot rotate away?
You can rotate away all of them, actually. So this is what I was saying. If you
rotate away everything, there's no Nelson bar.
No, in the absence of the explicit breaking in the first and last sides, just take the clockwork before you break it at the edges. At this stage, you can there is no pseudoscale. All the waves are zero, so you don't have any CP spontaneous CP break. Then I am adding some on top of this explicit breaking, as you do in a Relaxant model, at the two edges, and then you have two phases, or maybe eventually you will see. It's just you have these two quantities, so it's only one field, of course, and both of them get order 1. But
it's okay, but not every field corresponds necessarily to CP evaluation. How many? Can you write down invariants that you get? CP, non-rephasable invariants.
Non-rephasable in.
Yeah. Well,
so this.
Probably here is going to be something simpler, I hope.
So I would be, when I will write the explicit model, it will be very clear you can't rotate away the phase. This I can say. But before I break it at the edges, there is no phase. This is what I'm saying. Now when I'll add the back reaction and the rolling sector, when I write the model, before that it's hard for me to, I mean, I don't know if I can write in, but I can, I think, convince you that there is a real phase. So this I will show, I think, quite properly. Okay. So. Okay, so let me start with the first site. So you have okay, yeah. So you have the 4 Yukawa terms. Where the phi I should write in this. So then I have for the
denominator of the phi over.
It's a scale, which I call lambda n. Okay. This is a high scale. So maybe I won't write these brackets all the time. It will be clear from the notation because it takes too much time. Okay, so similarly there is for the 2 quarks, which I'll come to, but let me now stick to these 2. So you have the charged lepton and this is the phi 0, the first site. And as soon as the phi 0 gets a wave, I'll write it as let's say f over this. You can show that when I project to the Relaxant mode, will just become this, and this. So right now it's not clear. This phase cannot be rotated away, but this will give me something like f over square root 2, what I called e to the I theta 1, this one. Okay, so so this is what I get. So I can now, if I call epsilon n, let's say f.
What is pi tilde?
No, this is. I'm so sorry. This should be h here. It's just to make.
Okay.
It's just to make the Higgs, the conjugate. Yeah, it's just. Sorry, there's no phi tilde. Okay, so yeah. So and right now I'm using only positive charges. In the quark sector, I'll use negative charges also. So then I'll tell you what happens. But so let me call this epsilon n. And then I can just replace this thing by epsilon n. And there's actually also a phase, but yeah, okay, let me write the phase. Theta 1 raised to this. And similarly here I can write okay, where epsilon L is similarly defined. Okay, so now I want to talk mostly about the neutrino sector. So about the charged leptons, all I'll tell you is it's very well known how to, and I will explain how you go from these charges to the masses for the quarks anyway. So I'll be brief here, and I'll say that if you give the charges, for example, this charge assignment, so you kind of need some big charges. Then this can explain the masses of the electron muon top. So, and I will do this quite properly for the quarks. So it's not very. So this is all I'm going to say. But now the interesting sector for us is this lepton sector.
Sorry, one question. And the mass of these new furnace, the forgotten furnace, are somehow related if you're cut off, because otherwise when you.
So I have no new. This is just the right-handed neutrino. That's all I've added. So you are right that to UV complete these operators, I would need new fermions, but those will be at 10 to the 10 at the scale f. So it is by definition bigger than f, and you will see from the bounds on f that for us f is around 10 to the 10 at least. So yeah, there are some, or I mean, there are other ways to get this. I don't know, so even string theory or something can give.
Your cutoff is around 10 to the 8 GeV, right?
So I'm distinguishing between the cutoff to generate this operator and the Higgs cutoff will be smaller. This lambda, these are all different right now. Okay, and the scale of the. So yeah. Okay. Okay. So right. So far. Yeah. So let me focus on this first term here, and I mean let me. Yeah. So this. Yeah. So let me write it with the full relaxant field. So the first term here is something like. Let me now go to epsilon n times e to the I f to the Li plus h. So this is the first term, and so far I have not broken my U1 symmetry. Everything preserves the U1 symmetry. So now what I'll do is I'll just add Majorana terms for these sterile neutrinos, and here I'm going, and this will break the symmetry. Here I will be able. Okay, so let me tell you what potential. So once you break the symmetry like this, so the U1 symmetry, so phi is massless till now. Yeah. Okay, the shift symmetry of the phi. So you break it obviously because you're not balancing the charge of the n by powers of e to the I phi. You're explicitly breaking. Otherwise, you should have some e to the phi ni plus nj or something. Okay, so I break it by this.
Are these charges of n?
Of n, I haven't specified, but the point is you will see that once you integrate out the n, you get the Weinberg operator, and I mean this is what we are doing right now, but the final mass matrix of the neutrinos depend on the charges of the L. The n kind of factorizes out. So, but for the back reaction, I'll need charges of the n, so it doesn't matter too much what the.
is essentially for the lambda, capital F over capital.
This M?
Yes.
Okay, so what I'm assuming that my Frogat, which is, it's a very good question, that will completely destroy the mechanism, but I'm assuming that the Frogat-Nielsen, no, there's a symmetry. The Frogat-Nielsen preserves lepton number. So then this is not allowed. Even if you put powers of e to the I phi, this still breaks lepton number. So then I break lepton number softly only at what will turn out to be the weak scale. So this is what prevents those dangerous terms.
No, but I try to understand where these masses come from, and maybe they would do it.
Yeah, I mean, this I cannot have.
From the cutoff rather than some random mass which is significantly smaller than the cutoff. So essentially,
This,
you introduce. So you want to solve all the hierarchies, but you introduce a new hierarchy.
but this is what I'm trying to. This is technically natural. That's all I can say.
It's technically natural, but also the entire flavor is technically natural, so there's nothing to explain. But we can start from this.
No. But this is a soft.
Exactly my question.
Is dimension 3 referring to now? I'm talking about.
Okay, so if you, I have nothing much more to say. We just softly break it at the weak scale, and maybe you can imagine that this comes from the wave of another field that breaks the U1, blah, blah, blah. But I mean, the point of view here is think of this as an accidental symmetry that is broken only by M. Okay, so this is what I have, and the potential I'll generate is you can do Coleman-Weinberg or and then you will see. So now let me call Ynij equal to this is the final entries in the Yukawa matrix, epsilon n to the Li. So let me call this Yij, and let me so for the purposes of experiments and taking an anarchic Yukawa, although I don't need it, just using this to simplify my what I'm going to write, but you can assume all of them are order y. This is not a bad assumption. I mean, but it's also not necessary. So if I do this, then it comes out, just to give you the scaling, to be something like okay. I would also like to say here I'm cheating a bit because in our real model is more complicated. But what happens is because there are there are some technical issues like two loop effects can spoil, like you can close the Higgs loop and so on, can spoil the relaxant mechanism. I can go into those details later after the talk, but it's basically this is kind of a it's effectively what we have, but so we have a more complicated and a more ugly sector which effectively gives you this, and this will give you the potential, but in that sector you don't have these two loop problems. Also these arguments I'm skipping will tell you that M is less than a few TeV, and so in this complicated sector if the scale f M is less than few TeV, everything is fine.
Is M related to the Majorana mass?
Yeah, this is let's say order M. It is the M. Okay. So yeah, I mean, in general, you will have some like matrix. You will have some Yij. It's like the Y and M.
So you get a bit of seesaw, and then you need a large Frogat-Nielsen contribution to get a neutrino sector.
Yeah. So this is a very so okay. I will mention. So now you see, I have this. Now you can also integrate out the n and get the neutrino masses, which will scale like as usual. Okay. Now, as Pedro is saying, that we don't have m equal 10 to the 15 GeV, but it's not so bad. So because I have Frogat-Nielsen, so I can have small Yukawas. With m equal 1 TeV, you will see that you need so this y, as you will remember.
This is capital Y now?
Oh, sorry. This y and this y. These entries of this Yij.
These Y's should be order 1, right?
These y's are order 1. So what I'm trying to say is take these y's. Okay, I should say capital Y. Let me say that all of these the entries are order y. So I'm just to be y is the how big a generic entry of Yij is, not this small y. So this is a small number. So instead of writing the matrices, I'm trying to write the scaling for you. So this has nothing. So I should write big Y.
There is one scale which is the Yukawa matrix, and there's one scale which is Yukawa matrix times epsilon.
Yeah. So this is the one with the epsilon. This is the one with the epsilon. So the Y here goes as epsilon. Yeah, I just used a bad notation. Sorry, L plus N or something. Huh?
Times the other y.
Yeah, times the other y, which is order 1. Yeah, that's Yij. And yeah, exactly. So this y is and some element of this Yij. Okay, so now as Pedro is saying, this m is not 10 to the 15. So now if you do this calculation, you will see that what you need is y roughly order of 10 to the minus 6 or something, which is not so bad because already you had an electron you cover which was like this. And you will see that the charges you need for a TeV scale m are, you can do it with less than 10. So in other words, if you said that I don't want charges of 30 or 40, and then I want charges less than 10, then what is the seesaw scale I need? You will have ended up with around a TeV. So this is not so bad. So the fact that the relaxant gives you a TeV around 10 to the minus 6. So you can see if y is order 1, this is like 10 to the 15. Now if I go to 1 TeV.
No, for back reaction.
Oh, for back reaction, now I'll tell you what the back reaction is. Back reaction, I mean, you don't, you can have any back reaction. It's just that if it's small, you need a big clockwork chain or something. So I mean, in the original model, so I will show you, in the original first model, the back reaction was from lambda QCD, and we have something of the same order. I will show you. So now I can see what my back reaction is. So the back reaction scale, let me call it y square v square m square. And you can see from here, you can now write this as m nu times m cube. So there is 16 pi squared because it's a one loop effect. And this gives you around something like 200 MeV or something. Yeah, you have to do, roughly speaking. So this is our back reaction sector. Okay, so so now so this is the first part of the leptons, and the nice thing to me is that we have no electroweak, so there is no electroweak charge state at the weak scale, because in these loops to generate this you do need electroweak, but they are the standard model lepton doublet. So this is a model with only sterile neutrinos at TeV scale, so it's even harder to see at the LHC. Okay, so this is.
You haven't told us yet why n cannot be larger.
Okay. This is no, I haven't told you.
Will you tell us or not?
I can tell you.
Not to.
Yeah, it's just that at the moment the way I've written it really doesn't work, because you can close the Higgs loop, and then you can get a contribution much bigger than the back reaction, which will always exist, which will not need the Higgs wave. On the other hand, so what we'll have to do is we don't have this. We have a more complicated sector which gives me this. So we have like we add some more neutrinos, and then you integrate out some of them, and you get this. And in this sector, you can show that there is no UV contribution to the potential, because you just need too many masses to break the symmetry explicitly, and then there is no divergent contribution. So this is really to be stable under two loop. But even in this sector, this won't work unless m is less than a few TeV. Okay. So, right. Okay. So, right. So now let me go to the quarks, and so now there's some real subtlety in the quarks, and maybe. Okay, so now let me write quickly okay, I don't have too much time, but I'll try to. Okay, for the quarks, okay. So for the quarks, again, I write similar terms.
different?
Okay, so this is no, you don't need to. They are all the same order, except that you will see that the lambda up and lambda. So I could have used the same lambda everywhere, except that the lambda down needs to be roughly twice the lambda up when you try to fit the masses and all this, which I don't know. So this is a hidden thing which is true. So I could have used the same scale everywhere and a different scale just here. And you will see. And you can actually have different scales because it's different vector like fermions you integrate out and so on. So a factor of 2 I think is fine. Okay, so now I have these two. And now when I again set the phi to its wave, so this sector doesn't break the Froggatt-Nielsen at all. So I don't care about the physical phi, it gets no potential. But what I do care about here is the phase that is in the Yukawa matrices. That is here. So there is a phase, so it's like epsilon u e to the I theta. And there is a phase epsilon d e to the I theta. When I will substitute
These are
theta 1. These are both theta 1. Now the problem is because I want a Nelson bar model, I should make sure that this phase is not giving me an arg det of the mass matrix, which I can rotate away to theta. So maybe I have to make sure there is no theta QCD at this point. And generically there is. But let me see how I can remove this phase from these two Yukawa matrices. I can do it. What I can simply do is the transformation, sorry, not L. Qi goes to e to the I times theta 1 Qi. And similarly for the u and d, the charge of u I times and similarly for the similarly for the d, and you see if I rotate these q's by these phases, I remove the phase from here, right? Because this is just had the phase e to the I theta raised to the power of this plus this. Now I can rotate it back and remove this phase. Now the problem is in trying to do this, I can really remove the phase everywhere, and it seems that it's not a physical phase, but this is an anomalous rotation. So what you will do is you will generate. What this does is it generates a theta QCD, which is given by something like this, where n is the anomaly coefficient. It's the sum of the q charges plus the u charges plus the d charges. So you see, it cannot work unless, and this is another big assumption of, or I do not know, another requirement, this U1 is anomaly free. So if the U1 Froggatt-Nielsen has no anomaly with, no triangle anomaly with QCD, and this you can do by arranging the charges so that this sum becomes 0, then you are safe. So now the question is, can I find charges which give me the right quark masses and also are anomaly free? And the answer is you sort of, I mean, it's not, okay, let me show you what charges almost work. Not all, I mean, I will show you in what sense it's almost. So we need one of these y's to be 5%. That's all, that's the only little tuning in our model. So one of these y's, a fixed one, the yu12 to be precise, has to be order 5%, then we can reproduce perfectly the masses and mixings. Okay. So let me tell you, let me show you this.
It comes from the domain of integer charges.
Yeah, I mean, we took integer, but sorry, what? Yeah, we took integer charges, but maybe we can also do it fractional. But for one element, I mean, yes, you can do the element we need to tune. You can put another U1, another spurion, but this is too much for one element, I think. But let me.
But if you couple to different sides of your chain,
Yeah, maybe, but
hierarchy, no?
I guess, but but you see charm up, charm and top, and then I have the down, strange and bottom. Okay, so we choose these charges. The charges, so as I will show you, I mean, for general charges, the matrix you get, to diagonalize it parametrically in powers of epsilon is very hard. So you have, but it's very easy if the charges have this nice pattern that they decrease with the generation index, like it does here and here. And this is what people usually take. Here we do not have that because we need negative charges. Also, I should say that whenever this sum is negative, of course you cannot raise phi to a negative power. So what you should do is raise phi star to a positive power whenever this sum, this qi plus dc or uc is negative. So this is just to tell you that you can always, even with a negative charge, you can generate a Yukawa by using phi star. Okay, so now the problem is, okay, now let me show you the down. So the down sector charges are really what is commonly taken. So there is nothing special about this. So what do I get for the down Yukawa? And then it will be clear. So the down Yukawa is just epsilon qi plus dj. This is the matrix. I'm not writing the small y, but you should imagine. Okay, I can write it. So then you get this. So this is very easy. It's 3 plus 2, 6. 5. I'm not putting the d here. Maybe I'll use a. Yeah. No, it's okay. Yeah, I can't read the chart. 4 epsilon squared.
Thinking of the noise one.
Okay, so this matrix has a very nice form, and this is because I followed the rule that the charge decreases with the generation index. The nice thing is that if you look at this row, this is the biggest element, then this is smaller, then this is even smaller. Same here, that this is smaller. So this has a quasi-diagonal form. It is like a diagonal matrix with some small mixings added. So in this matrix, I can show you it's just a matter of diagonal, like some algebra, but if you want to quickly know how to read off the masses and mixings, for the left-handed, you just need to look at the upper diagonal. These are more related to the right-handed rotation. And in the standard model, the CKM is made of the left-handed. These diagonal, because it's almost a diagonal matrix, give you the masses of the mass eigenstates. So roughly speaking, if you choose epsilon d equal to, not roughly, it's pretty good, you will see. If you choose epsilon d to be 0.5, this gives you roughly this has a wave everywhere. This gives you roughly the down mass up to order 1 factors. This will give you the strange and bottom. Now to read off so now what about the down rotation matrix, the left-handed down rotation matrix? The 2, 3 element is just this over this, is order epsilon square. The 1, 3 is order epsilon cube, and the 1, 2 is order epsilon. And this already has has the correct CKM structure. So the CKM will be made out of VDL and of course VUL. If both VDL and VUL have this structure, then the CKM also will have this structure. But okay, so this is what I have. So the down sector works perfectly just because I've used the usual thing. Many hundreds of papers have already used this kind of charges and it works. What about the up sector? So it's again the same except that you have up here. So this is.
Don't do that.
Okay. Sorry. Sure.
There's also white.
Let me now go to the. Let me now go to the up sector with those charges. So the down sector is just standard Froggatt-Nielsen and everything works out. For the up sector, you get epsilon u times v qi plus ucj, and these are the charges. This is my up sector, and now if I write down the matrix using those charges, I get let me go. Yes. So you get epsilon up to the 8, and so this is one thing that you were asking whether I choose the lambdas different. So to really, so here you see I have use epsilon d equal to 0.5, and you will see I'll have to use epsilon up equal to 0.2. So in this sense, the lambdas are not even factor of 2, are a bit different to fit the masses. But usually they even take the same epsilon. But I think it's totally fine to take slightly different epsilons. So this is what I get. Now you see this has almost the right form. So this also goes as 1 epsilon squared epsilon q, which will give you the right VUB and VCB. So this will, or the 1, 3 and 2, 3 elements are fine. You see the masses with epsilon 0.2 will give you the up, charm and top mass. The problem is that here you are breaking the quasi-diagonal form. So here this element is actually bigger than this. So in this sector I will have a big rotation, and if you really do it on mathematics, you will see that the up and charm get mixed and get flipped and so on. So what you really need, so this doesn't work because of that reason. But remember there is a y here. And now if I tune the y to be ordered epsilon u squared, which is 5%, because epsilon u is, so if this is 5%, then it works perfectly again. Sorry?
Order 1 number.
So this is has to be an order 1 number. It's a Wilson coefficient.
Would you like to say it's 0.05?
It is 0.05. It's a dimensionless number. Okay. So if I tune it to be instead of 1, I tune it to be 5%, which is hardly any tuning. Then no, it's not hardly. So this is the one parameter which is not order 1 in our model. So this okay. So yeah, maybe that's too strong a statement. But okay. So this is what I need, and then you will be fine with the up sector also. So the problem I'm getting is because the charge of, so usual Froggatt-Nielsen, they will choose only positive, and the charge here is decreasing here. So you see, usually if this was always decreasing, you will always get the off diagonal is smaller than the diagonal. But here my charge for the up sector actually increases with the generation. I mean, initially we also didn't realize, but then we see that there is this little trick that makes it always work.
And this was so that you get the Nelson bar.
This was, so yeah, which I'm now coming to. So this was because I want the sum to be 0, so I need to have some negative charges. So this is the price I have to pay. Of course, what I can do is I can do it with positive charges and then say something in the UV, and we will have new fermions in the UV. They cancel this. Or I can have just a bare theta GG12 term, which I can say for some reason it's this U1 is anomaly free, and I've integrated out one of the fermions, which I see as a bare theta, and this is another approach. But if you want to see the cancellation in the IR, this is okay. So now yeah, I won't take very long for the Nelson bar, because it is I have rubbed my nice. Okay, so okay, maybe sorry, I shouldn't have rubbed it. Okay, okay, this is, I think, something that can work. So now I've described to you the first side, and now I've generated all the quark masses and lepton masses, neutrino mixings, everything, but everything is real. There is no phase. So I have not explained the CKM phase. So as I said in the beginning, in the clockwork chain, the last phi n would give me the phase. Now I'll write a Lagrangian, which is a very well-known Lagrangian. It has been studied and it works and so on. It's basically a Nelson bar model, but the original model of Nelson, there was some attempt to make it compatible with SU5, so it had more matter content. So this is a model which is more minimal, and it was proposed by Bento, Branco, and Parada. So I will just replace their scalar with phi n, and you will see that it. And I can quickly. So let me now go to their model. It will really take only 5. Not long. Depends. Okay. Depends. Okay. So this is on the last site. I have a Nelson bar sector. So what I do here is I add a new vector like fermion, a vector like pair F and Fc. So my Lagrangian is something like this. And okay, maybe I should tell you also the symmetry. So then I impose an additional Z2 symmetry under which the phi n goes to minus phi n, and the F is also odd. So a Z2 under which F and phi n are odd. Everything else in the standard model is even. So now I have this, and then I have.
But then how do you write the Clockwork?
Yeah, so you are breaking the Z2 just like you're breaking the U1 at this site, and no, you can still write the Clockwork because if all of them are Z2 odd, you can. So if all the Clockwork fields are Z2 odd, you can write. But then the problem you will have is the first site, unless you raise it always to even powers, will break the Z2. But this Z2 breaking to be communicated from this site to here is an extremely small effect. So there are much bigger. So let's say all phi i's are odd, and I break the Z2 also at the first site. But there are much more dangerous effects here that can spoil it than this effect. This will be suppressed by epsilon to the n. Okay. So then I have this coupling. So I involve only the down sector for this Nelson bar. There is no up sector. This is the usual case. So. Okay, so this is to make this Froggatt-Nielsen invariant. So this is my Lagrangian, and you see that if you turn off one of these, you still have the U1. But since I've turned on both phi n and phi n star coupling to this thing with the same charge, I have obviously broken my U1. And this means that I will generate, okay, and this plus, of course, you have the down, so these are after I've given it the wave, and so this is the down coupling. So I have this, so I break the U1 because of the presence of both Y and Y tilde, and this actually gives me a rolling potential. So if you substitute it, that phi n is f e to the I phi over big F. So if I substitute this, I get a nice potential which goes as y f tilde squared over some squared. And now the reason I could not have put this in the first site is because this goes as this really goes as roughly the scale of the clockwork, or f squared, let's say, and cosine phi over big F. And I also generate a term with the Higgs because I also have the Yukawas, and this is very easy to see. You just close the F and D in a loop and you will generate these terms, or in this case plus you get and the two, and with two standard model Y's you also have this. So I can generate the rolling potential. That is not so hard. Now I want to show you that this actually solves the strong CP problem if everything so far is real, and because of our trick of choosing an anomaly free U1, I can rotate away the phase and make everything real here. So now very quick. Now what happens is once phi n gets this wave, and as I said, this you can replace now by the theta 2. If you remember, the theta 2 is the this argument of e to the I phi over big F. So so once I do this, now there is a real phase that you cannot rotate away, because you have both here, and you can check that you cannot rotate away this phase because you have both phi n and phi n star here. So now this phase, so now what happens is that I have this phase, and but also this phase is not entering theta q c d. Why? Because let me write the mass matrix now in this. So the mass matrix is something like this. Mu, there is the 3 by 3 down Yukawa here. There is something I'll call BF, which is, and 0. This is 0 because, okay, I told you about the Z2, but I didn't tell you that the term I'm trying to prohibit is this, because FC has exactly the same quantum numbers as a standard model down singlet. So I prohibit this term. So if I prohibit this term, that's why I have a 0 here. Otherwise, I will have something here. And this is crucial because now you see, and what is B? B is just this thing. So B is just this whole thing, okay, this whole thing, which is the coefficient of this, I call B Fi, okay. So it's a row vector. Now you see that if you look at the determinant of this matrix, the determinant of this matrix is mu times the determinant of y minus 0, and everything here is real, so this is real. So there is no argument of this, and you have no theta q c d at tree level. Now, of course, there is no symmetry that. Okay, so let me also see now that show you that you have a CKM phase, and then I'll tell you how. So very quickly, if once you integrate out the F, the effective 3 by 3 down matrix gets modified. So I will look at the combination MD dagger, because this has all the information of the down mass eigenstates and the CKM, because MD dagger MD is related to the right-handed, so you don't care about that. So this has all the information you need. If you keep this unchanged, you don't change any of the CKM or masses and so on. So this let me call it effective. This is not YD times V, as you will see. So this is given by V squared YD IL. So something like this, and this B is complex because you see that once the phi n will get this phase, this B is complex, and there are some more conditions. If only let's say if in these Y's I only couple to one generation, it won't work, because if only one element of this B is non-zero, then you will see BB star will become real again. So I need at least two fermions to have the same order of coupling, and I also need Y and Y tilde to be of same order. So for a pair of fermions Ij, I need Yi tilde equal to Yj tilde equal to Yi of the same order. And that is easy to do in our case, because you will remember that the down, you won't remember probably, but the down charges was 3, 2, 2. They're up there. So the last two generations had the same charge. And so now if I choose the F charge appropriately, first of all I can make this coupling smaller, which I need, as I'll show you, and also I can make them to be the same order for two generations, and that will give me a real phase here. So I can tell you that we have computed this numerically for random numbers, and we do generate an order 1 phase. Now another serious concern, which has been dealt with in detail by the original authors, is what about one loop effect, two loop effect, because there is no symmetry which is protecting theta QCD here. Now for that you can show, and there was a recent paper by also which did very nicely by Dine and Draper, which had the same model, and and also you can do that there are one loop threshold effects which can generate a theta QCD for you, and this to be fine with this. If you want this, then you just need this So this is the last thing I'm going to say. So let me call this product y times this, this full product, let me call it, not with the phi, y times the epsilon. Let me call this product, let's say G, and GFI and GFI tilde. So as long as this G, Fi and G, they have to be the same order also for the CKM, is less than about 10 to the minus 3, you will see these effects go as the fourth power of G times 2 loop factors. So even 10 to the minus 2, you do not generate a big enough theta QCD. So so that's so that finishes the model. If you, I wanted to talk about phenomenology. If you have, so okay.
So, questions?
So how do you test this model?
Okay, so now I can tell. Okay, so in 1 minute I can tell you that this phi has flavor of diagonal couplings, and it's a light guy. So it has very strong bounds from things like k to pi phi, and this is what puts a bound that f has to be more than 10 to the 10 GeV. And you also have strong bounds from mu to E phi, not mu to E phi, mu to E phi gamma and so on, which are a bit weaker, which tell you that f, these are all tree level processes, there are no loops. So really the only suppression you have is by f, 10 to the 8 GeV. So this tells you what f you need, and we are investigating the constraints more now.
Okay, let's thank him again.
Yeah.